Next up is Filip Strömbäck.
Close enough.
Active DSU, dynamic software updates for active functions.
Thank you. So to set the stage for, this idea is, imagine you're writing some kind of simple threaded application. So you want a thread that processes messages, incoming messages. Doesn't really matter what they are doing at this stage. We have a message queue, we get messages, and since I'm developing this thing, I'm printing them out before I process them. And assume that eventually, either if I'm in a live system and I'm like exploring Onwards, or if I have actually deployed that one and want to change it, I want to update it so that I want to be able to send messages to threads to ask them to exit. And I simply do this by adding some methods to this object. And as you can see, I set an exit flag in the loop. And interestingly, I also have some logic to try to migrate any remaining messages to other threads towards the end. And there are techniques that will kind of allow me to do this, and I can use dynamic software updating for it. And these are useful both during development, because you can do quite flexible live programming with them, as we shall see. And we can also use them in production. For example, if I want to apply this thing without having to shut down my program and start a new version of it, for example. The interesting part about these two things is that while like the mechanisms are similar, there are slightly different requirements. For live programming, for example, you want minimum effort in order to be able to apply an update, because otherwise it's not worth it. You can just restart your application. While in production, it's very important that the update is correct, because otherwise my program will, or the updated program will crash in production, and then I'm very sad. In this talk, it will be a bit more geared towards live programming, because as you can see, it's a bit experimental at this point, but I hope to be able to get to something better. In particular, as I've written down there, we need two major things in order to apply an update. We first need to think about any changes to data structures on the heap, for example. And we also need to consider control flow. This talk will focus on the second one, because there's quite a lot of research in the first, and we can actually use that, as we shall see later on. And the goal I'm proposing is, as the title says, Active DSU. So the goal is that I want to be able to update these things without waiting for something to happen. And to be able to do that, I need to be able to update active functions, that is functions that have stack frames on some threads stack. And ideally, I want to be able to support large sets of updates, few annotations, and with minimal runtime overhead apart from the actual update. The first thing we should think about is, where do we allow updates to happen? If we imagine that we just pause a program at any point and look at the call stack, what we will see is that all stack frames except the topmost one will have the execution paused at a call site. And this is nice, because then we only have to consider call sites. Call sites are quite nice in the ABI also, because they are kind of well defined in where things can live due to the ABI. But for the topmost function, we can pause essentially anywhere. However, if we allow ourselves to execute some bounded amount of code, we can like advance the program until we get to a call site or a back edge, so that we get to a loop header. And that way we can reduce everything down to that we only need to consider call sites and loop headers, which is much simpler than anywhere in the program. So for the example that I will be using here, let's just consider that we will be updating the program when we are waiting to get a new message inside the get function. And that is good enough for our purposes here. The first step we can do is as simple that we need to simply relink the program. That is, we essentially run the program through the linker again, but in process, of course, which sometimes needs some kind of interactions and stuff. This would kind of work, but what will happen is that for active functions, for example, the main function here, when we return from our get function, we will return into the old version and continue running there. So what happens is that we won't see the changes I made to the main function. However, it will, of course, call the new versions of get, debug, print, and process if I change them. So this is like the fundamentals, but it won't really solve this particular problem of active functions. An interesting solution, or partial solution to this one, is from the tool that's called Ginseng. It actually automatically extracts loop bodies into separate functions and uses the same approach. And that way, we get this interesting behavior that for the first message that we receive after the update, we'll run the old version of the loop body, but then we will return back to the main function that is down to the left there. And then on the next iteration, we will enter the new version of the loop body. So we kind of get into an intermediate state between the two versions, because as you can see, since I cannot change the main function as it is there, the call to migrate will be skipped. And there's also some problems with, as it is implemented, we cannot really add the exit variable. We can, of course, refactor the loop body to fix it in this particular case, but not in general. One way to avoid this kind of difficult to reason about behavior of these, like just relinking, is that we can wait for quiescence. Essentially, we wait until no updated functions are active, and then we apply the update then. That makes everything much easier to reason about, but waiting for quiescence is in general unbounded. And in this case, we will not reach quiescence because we updated a function with an infinite loop in. So we cannot use this to update this active function. Another interesting solution is to introduce update points, which is done by a couple of tools, either by manual annotating your code by saying this is a safe point to update in, or by some profiling. The downside of this is, of course, that you need to do some like preparatory work. Imagine in a live system, you don't want to be very much upfront in order so that you can actually be able to continue exploring stuff. So that's the main downside with this thing. And also, depending on exactly where you have your update point, you can get these kind of delayed updates. So for example, assume I have my update point at the dashed line. I will get similar behavior to Ginseng is in the sense that we will run the old version first. Then when we get back to the next version, iteration of the loop, we will kind of save the relevant state, shut down the program, start it up again, and reinitialize everything. And then we can continue running the new thing, which is not exactly what we want. And you can imagine there's all kind of interesting code that we need to run there and so on. And I would prefer to avoid that. So to get to the solution finally, remember that our goal is essentially that we want to get, when we return from the get call, we want to return into the new version of the function directly. And to do that, we essentially need to rewrite the call stack. So what we want to achieve is that we want to go from the call stack on the left to the call stack on the right. And what makes this difficult is that in this example that I have here, I need to introduce a variable there. So I need to grow that stack frame. And to do that, I need to move the other ones upwards. And of course, I could just memcopy it, but it wouldn't work because, as you can see, I have many pointers to stuff on the stack that will be incorrect. And I will need to know all of them in order to be able to do a good job here. And that's quite difficult. One way is to do as the tool upstairs that injects code to essentially serialize the stack into a separate representation, modify it, and then like reinstall it in a sense. But that introduces quite a bit of like extra code, and again, you need to be upfront by tooling. So what I'm proposing in Active DSU is that instead, why don't we just replace the return pointers on the stack? That's actually quite easy to do because the ABI essentially mandates where they are. If you look at exception handling, for example, the dwarf standard says that the variable offsets are specified in relation to where that is, so it's quite easy to find. So once I've found them, I can just replace them with a pointer to a stub that I generate. And what happens then is that this stub will essentially act like a callback from the system for when we would have returned to the main function. And the nice thing about that is that when we return to the main, or when we would have returned to the main function, that one is the topmost on the stack. So now it's quite easy to actually just grow the stack frame, rearrange the variables, and then we just jump to the new version. So I have an animation for it, of course. So I can just add the exit variable, and then finally I jump to the proper location in the new version. And this is quite nice also because after the update, at no point I execute old code. So I can remove it immediately, and in essence, I'm sure that no old code runs, so that in case I have modified any heap data structures, they won't be touched by old code. Then the question is where to resume. And for that, I have an idea of call site mapping that works at least for comparatively simple cases. The idea is that I extract a very abstracted version of the control flow of the function. And remember from the start, we really only need to consider function calls and loops. So that's the only thing I have in these abstracted versions of the control flow. And as you can see on the left, we have something that calls the constructor of a message queue. Then we have some loop which calls get, debug, print, and process. And what I do is that I essentially run a version of the diff algorithm on these. It's recursive because I have nested lists and all that. Details are in the paper. But it will produce a mapping like this. So in essence, if I updated the program during the call to debug print, we will just return to after the get function and resume from there, for example. And this is what it looks in the source code that we are in. And at this point, at least with this kind of small changes, is quite intuitive, at least. So the big question is, does this work? And to answer that question, I implemented a prototype. And I implemented in a language platform that I have developed that is called Storm. It's an interactive system. And the language we're using here is Java-like system. Actually, this code is in that language. It's compiled language. And this is important because it kind of feels like Python when you're interacting with it. But it is compiled, so I'm actually doing stack rewrites. I'm not cheating by just putting everything in a hash map and calling it a day. We have garbage collection, so I don't really have to worry about when I deallocate stuff. That's a simplification. And it already had support for relinking programs quite cheaply. So I kind of got the first step for free, or because I implemented it before. And by adding Active DSU, I'm now able to update active functions, and I'm doing like simple migration of data. We could probably put in some more complex methods from like other more sophisticated tools and so on to make it even more competent. And I should mention that for now, I only do non-topmost functions. It's just a matter of engineering, not an inherent limitation. And what do I need to be able to do this? Well, I have essentially implemented it inside of the compiler process because it's an interactive system. But as you can see, I have drawn it inside of the, together with the new function, because what it takes as an input is a quite detailed description of the new function, like low-level intermediate representation. It has access to all type descriptions and the compiled version of it. But from the old function, I don't get that much data. So this kind of opens up for me to look at a binary with the debug information and kind of update it there. So the metadata I had and needed to add was information about all the call sites. I kind of had that because I garbage collect these, so I need to update them. I had to add information about back edges, which you can find by disassembling the code in binaries. And I added information about named variables so that I can shuffle stuff around on the stack. But all of these should be possible to extract from a binary if you have debug information at least. And with that said, I think I can try to show you this prototype in action. So what I have here is that I have a small implementation of the code that we saw. And if I start this one, you can see it starts iterating, and it's printing debug print when I call debug print and process things. And the messages are just numbered, of course. So what I can do here is that I can modify it to the last one. It's just a macro in Emacs. It's nothing magic. And then I can ask my system here to update this one. And let's say that all messages above, what will it be, like 35 or so, will be exit messages. Let's do 40. And then I tell it to update. And now you can see it continues running, no debug prints. And then we exit when we expected to, and we even got the call to migrate in as we expected to. So the approach works, at least for these simple examples. And just because I got a review comment about recursive functions, of course, we can do stuff with recursive functions also. So this is just, this log begin is what's print stuff. And as you can see, I've completely forgotten to do the end condition. So if I add that on level 20, yeah, that's fine, and update it, we can see that it continues running until we get to 20. And then we terminate as expected, and we even got this log end call as we would have expected. So this kind of works, at least for these simple examples. And I can just quickly give some details on how this particular implementation of a stub works, because it turns out that you have to keep, like, it's a bit tricky to get it right, especially if you want to allow exceptions to go through functions that are replaced with stubs. But essentially what I do is that I first update the stack frame to get some extra data so that I can spill registers and so on, so I don't have to worry about preserving all the registers. Then I can initialize new variables. And at this point, I can call constructors. I can do whatever I want because I have spilled like dirty registers and stuff. I can initialize temporary variables, because in some cases, when you're in the part of an expression, you have like temporaries that are pointers to a variable or something. And what I do in this particular implementation is that I actually copy initialization code from the new function until I reach named variables, and that kind of gets this past the address of a variable to the function to work. This is not perfect. There are cases I know it will fail. And then when I've done that, I can just restore the registers, shrink the stack frame back to the new size, and then I can just jump to it. So what is there, how to say, left to do? Well, as you can see, this kind of idea opens up to much exploration of what we can do, and in particular, this like trade-offs between how much should we do and how much gets confusing for programmers. This particular example I have here is probably an example when it works good, but you can imagine if I simply replace the entire implementation of a function with a new one, then one question you should ask is, what should happen in that case? And the second question is, how much can we do? Because in general, we cannot really solve that problem. And related to that is like, how can we show to users how they can reason about what happens in updates? And that's particularly important if we want to do it in like production systems, of course. In live programming, I mean, in my opinion, the worst that can happen is that your program crashes and you have to restart it. And we're still like kind of winning if we can have a 90% solution there in live systems. And then finally, it would be nice to combine this with more sophisticated approaches for like intelligent migration of data, but there are related work for that. And I would like to explore an implementation in Clang and C++, because like imagine taking a binary with debug information that the author didn't prepare for me, and then I can just run Clang and give it some kind of patch that I can apply. I mean, in essence, I don't see anything preventing that from happening, but there are things that will need to be worked out. So to conclude this idea of Active DSU, we can update active functions. We can do quite a lot of things, and opens up for exploration. We can do quite interesting things in this space. And I don't need extra code in either version, so the steady state execution is not impacted. The only cost is when we actually shift between these versions. And we can even do quite a lot of this like ahead of time. I don't have to have all the implementation in the like live system. And some details on exactly what needs to be done is in the paper. I can also mention that it's available at the website for the system. But I haven't done any precompiled releases yet, but you can find it in the branch that's there if you're interested. And that is everything from me, so I'm happy to take questions.
All right.
Hey, thank you for the talk. What happens if you make a modification that basically changes the past? Well, use this recursive example. You made the change just as quickly enough before it reached the 20. What would have happened otherwise? Well, if your return is not there anymore, right? Where to return to if you remove the call?
You mean if I remove it, what the current implementation does is that it will map it to the start of the function and just run through the function. And what you're getting into here is a discussion of, first, what do you expect would happen? And then the question is, what should the system do?
Well, I'm experienced with Smalltalk and Squeak, and well, you update the topmost function, right? And everything else is the old version. And this seems to be working pretty well. Of course, it has limits, but I can't get my head around rewriting the past, so I would not know what to expect.
Yeah, exactly.
What the stack would look like.
And this is also an interesting observation, is that even though I changed the recursive function, of course, I'm not rewriting the past. The call will still have happened in the sense. So, for example, assuming that I make the condition on the recursive thing after 20, as you said, the call to 24 would still have happened. But what will happen is that once those calls return, the Active DSU will find a location to resume from in that function. And if you have removed the call entirely, then it resumes from the start of the function in the current implementation. If there is a call, even though you didn't execute it, it will appear as if it returned from that call. So that will still give some unexpected things would happen in some cases, but it's still better than mixing all the new code in greater extents in some cases, I think.
Thank you.
Thanks. Am I on? Am I on? Yeah, there we go. I really enjoyed this. It's been a while since I read about ginseng and upstairs and all the rest, and I was thinking during your talk, so there's always a bunch of assumptions about, what cases are known not to work, and there's often a bit of fuzzy areas like we don't know if there's things in this space where we haven't really articulated what will work, what we won't. The thing I was thinking of is if you have, if in the stack frame that you're resizing, if you have incoming pointers to that, maybe because you let a pointer escape earlier in the execution, can you deal with that? Can any system deal with that?
Yeah, that's actually a limitation I mentioned in the paper, but I tried to keep down to the allocated 15 minutes in the beginning. I failed and get 20, but it seems to be fine. But that's actually one thing that is nice about this language, is that I don't allow taking pointers to stack allocated objects, so I'm kind of saved there. I still have the issue with if you're returning a bigger data structure, the way returns works in many ABIs is that you have a pointer towards it, and you have to deal with that. And one idea that I have is, and I haven't tested this yet, is because you kind of know when you get pointers from that have escaped by parameters and so on, at least if you think one levels as a start, you can kind of detect that and allocate them elsewhere temporarily, because when such things will have changed, you kind of get the chance in both functions, or at least you can arrange to get the chance to fix it up in both functions. But we are talking about a can of worms here, as we are into. And that is a challenge with moving to C++, for example, because there you do it quite a lot.
Right. I would love to talk about this later, or actually remotely, because I'll have to dash off after my talk. But thank you. This is really good.
Thank you.
So this is really great. I congratulate you on the explanation of the related work. It's always nice to have that introduction, because the audience usually isn't as up on it as everybody else. And I also want to congratulate you on your courage for trying to make this work. It's really crazy, right? So
my friends tell me that when I show them this.
So my particular scare was when you showed diffing of the text before and after. And we all know that when you do a diff in Git, it can get it totally wrong,
Yep.
right? Especially if you're moving code around.
Yep.
So my question here is twofold. One is, do you experience those problems? Do you have any solution to it? And second, have you thought of, instead of doing textual diffing, using a structure editor, which can give you, much safer information about how the program actually changed?
Let's start with the second one, because that's what I remember most. In a sense, I'm not doing straight-line text diffing, but in an essence, that's what I'm doing, because I'm looking at the artifact of compiling the text. It would be very interesting to have this.
But that's even worse, right? Because now you're
Kind of.
you're diffing the output of the compiler.
Exactly. But what you're saying is, if you have input from a live system, or from the editor, from the history there, that would be great in these kind of situations. In the system I showed you, I do have Emacs integration, but it's only talking to the compiler. So I don't have that currently, but I think that would improve the situation if you know what has actually happened. So that is a great idea to improve this. But for the textual diff with things misbehaving, let's just call it like that, it goes into this idea of some changes are too large, and we're never really going to get them perfect. But there are certainly better algorithms that handles more cases. And I mean, this works for kind of simple cases, at least. That's the extent that I have tested it to so far. But there are certainly edge cases that I can improve with that. So you're completely right in that it will make mistakes in its current form, at least. And I will have to fix those.
All right. Future work, as they say.
Yeah, exactly.
More research is required.
That's why I have this.
All right, let's thank the speaker.
Thank you.